Hello everyone. Let's do our last example of checking solution. And this time, let's look at a partial differential equation. Although in this class, we are not going to look into the partial differential equation that much, but let's look at in this case. So that's our PDE, the partial differential equation here, right? And here alpha and lambda are some number. So here the lambda represent as some real number, alpha is also some number. The unknown function here is u. So my unknown function is u, and u is a function of x and t. So it's a two variable function. We're looking for what is my two variable function so that it becomes a solution. And then they give you two possible solution. And you have to check what your lambda should be so that it becomes a solution. What my lambda should be. So I'm looking for lambda. What is my lambda should be so that my u1 and u2 becomes a solution to this partial differential equation. So I'm going to do u1 and then you can check or do it u2. It's the same difficulty level. It's not too much difficult. So let's start with slightly easier one, which is E1. So let's start with E1. So I'm simply going to write E1 is E to the negative alpha square. Whatever that is some number. So that negative alpha square, think about some number 7, okay, as an example, times sine x. So I have to check that I have to figure out the uxx and ut. So uxx is the partial derivative with respect to x twice. So that's the second partial derivative with respect to x twice. And ut is the first partial derivative with respect to t. So I hope you all remember all your partial derivative business from calculus 3. So let's go ahead and do that. I'm going to simply, okay, so let's leave it u1 as e1, no problem. So let's start with the partial derivative of u1 with respect to x. I want to actually, so there's another way I can write u1 of x if you want. Same notation. So you're thinking x as the variable, t as a number. So this whole e to the negative alpha squared t is like a number. So I can copy that because that is just a number. T is like a number now because for this partial derivative, x is the variable and the derivative of sine x is cosine x. I have to do one more time because I want the second partial with respect to x. So let's do one more time. So that will be give you the second partial. I can also use this notation. So here, same idea. This is a constant. So I'm just going to copy that. And the derivative of cosine x is negative sine x. So I'm going to put that negative in the front. Okay. So I got my uxx. So in place of uxx, I substitute this u1xx, right? So that's my second partial with respect to x twice. Now I need ut. Let's do that. So my u1 of t, so I'm taking partial derivative with respect to t now. So t is the variable, x is like a number. So I'm looking at here again. So now I'm looking at here again, right? Now t is the variable, x is like a number. So this sine x is like a number because x is like a number. So that sine x, perhaps I'll copy that first. So let's copy that sine x. It's just a number. And think about the derivative of e to the negative alpha squared t. Remember, this negative alpha square is like a number. 1, 2, 3, 4, 5, whatever that is, right? So the derivative of that is negative alpha square e to the negative alpha squared t. Think about this. What is the derivative of e to the 5t? So that's 5 e to the 5t, right? Instead of 5, you have negative alpha square. Negative alpha square is like a number. So think about that as a 5. So that's my u1 of t. So that goes in place of u of t. So this one goes on place of u sub t. So that's the partial derivative with respect to t. So let's substitute and make sure the equality is true, and to figure out for what value uh, this is true, right? Let's look at it. Let's actually find out. So I'm going to substitute here, down here. This is going to be, so let me copy that question. So alpha square uxx equal to ut. So let's substitute. Okay. So in place of uxx, I substitute this. In place of ut, I substitute this. So let's do that. Equal to, in place of ut, I substitute this here. Are they actually equal? They are indeed equal to each other. So in this case there is no lambda. There is no lambda to. So this is actually true, right? You can they are actually equal to each other. So this quantity is actually equal to this quantity. They are indeed equal to each other. So we check. I mean, this negative, you can just bring it on the front if you want. Okay. So they are equal to each other. Okay. So here, no matter what my alpha is, this is always going to be a solution of the differential equation. In this case, I don't have any lambda to solve for. In the second one, this one, you do have a lambda and you have to figure out for what lambda this is a solution. Actually, let's do that. Let's actually do that. Okay. So I'm going to copy my u2 in the second page. Let's actually copy the u2. Let's actually copy it here. Now let's check the u2. u2, I do have to find my lambda. So let's copy the u2. E to the negative alpha square lambda square t. Remember, alpha, lambda, they're all number. So treat them as number. Sine of lambda x. So that's my u2. Okay. So I have to figure out my what my lambda should be. So this becomes a solution. Okay. So let's go ahead. Exactly the same way. Partial derivative with respect to x. This is a constant because t is a constant. So I copy. And in this case, the derivative of sine lambda x is cosine lambda x times the derivative of lambda x, which is lambda. I put that lambda in the front using the chain rule. One more time. The whole thing is a number because we're taking derivative with respect to x. And the derivative of cosine x is negative sine lambda x times lambda. I'm just going to put that negative lambda on the front, and that becomes negative lambda square, because lambda times lambda I multiply out and become negative lambda square. And let's do the partial derivative with respect to t. In that case, this is a constant, so I copy that sine lambda x. X is a constant now, and the derivative of this whole thing is, just think about this whole negative alpha square lambda square is like a number. Let's think about that as a 5. So that's going to be e to the 5t times 5. So so that's negative alpha square lambda square e to the negative alpha square lambda square t. That's it. Okay. So now let's substitute all of this information into the differential equation. So that's my differential equation here. Alpha square uxx equal to ut. So let's do that. So I'm going to do it here. Alpha square uxx equal to ut. So let's substitute. In place of uxx, I substitute this. So let's do that. So I'm going to put a parenthesis here. So that's my uxx on the top. So that's my u2xx that goes in the place of uxx. And this is supposed to be equal to, I have to make sure that's equal, ut. Where is my ut? Is right there. So let's copy that in place of ut. Make sure I copy it correctly. Okay, very good. Okay, so let's write them side by side. Okay, so I'm going to put this minus on the in the front. And in fact, this is always true. Okay, and they are indeed exactly equal to each other. This is actually for all lambda. Okay, so in fact, what we found out that for all lambda and for all alpha, both of them a solution to this partial differential equation. So we just check that this is indeed a solution. Wow, this is beautiful. And you can do it. You can always do it. Remember that. Bye bye.